So when I distribute, I end up with sine theta minus sine theta cosine theta. I am. I need a lot of people asking. So when I distribute, I end up with y is equal to sine theta minus sine theta cosine theta. So now I want to differentiate it. So now when I take the derivative, here's my dy d theta. Well, the derivative of sine theta is going to be what? Cosine theta. Minus. Now be careful, make sure you put parentheses or brackets after your subtraction sign. How are you going to differentiate sine theta and cosine theta? What rule do you have to use? Product rule, your big Z. F prime G. So I'm going to have a cosine theta times cosine theta, which is a cosine squared theta. Plus Fg prime. So sine theta times, what's the derivative of cosine theta? Negative sine. So a sine times a negative sine will give me a negative sine squared theta. So when I simplify this, when I distribute the subtraction sign, I end up with cosine theta minus cosine squared theta plus sine squared theta. I'm sorry? Remember, addition and no, be careful, because addition and subtraction are equitable operations. You would work order of operations from left to right. So in other words, you cannot substitute a 1 here. But now remember, I want to know where my dy d theta is equal to what? Where it's equal to 0. So I need to set dy d theta equal to 0. So cosine theta minus cosine squared theta plus sine squared theta. Oh gosh, now I gotta remember how to solve for equation. So unfortunately right now you do have a trig equation where you have more than one trig function. Is there a way that you can get rid of this sine squared? Exactly, use your Pythagorean identity, substitute out, take out your sine squared and replace it with a 1 minus cosine squared theta. Combine your like terms. I have a negative cosine squared theta and a negative cosine squared theta. So 0 is going to be equal to negative 2 cosine squared theta plus cosine theta plus 1. And again, I always like to factor with my leading coefficient being positive, so I'm just going to write this as 2 cosine squared theta minus cosine theta minus 1. So the question is, your quadrant equation you need to factor. Oh my gosh, all that shit to the back. How do you factor this? It's going to be what? If you're not sure what to do, you can do a substitution, take out the cosine, replace it in x. In fact, it is a 2x squared minus x plus 1. You don't want to see it in terms of cosine. This will factor into what? 2 cosine plus 1 and then a cosine theta minus 1. So I need to figure out where is cosine of theta equal to 1, where is cosine of theta equal to negative 1/2. So again, going back to your unit circle, what two quadrants where is cosine negative? Cosine's negative in what two quadrants? Second and third. So what's the angle in quadrant 2 that has a cosine value equal to negative 1/2? 2 pi over 3. And then down here in quadrant 4 would be, 3 would be what? 4 pi over 3. And then where is cosine equal to 1? Cosine is equal to 1 where? Yes, 0. So my three theta values I came up with, 2 pi over 3, 4 pi over 3, and 0. Are any of these repetitive? Is the equation of the line theta equals 2 pi over 3 equivalent to theta equals 4 pi over 3? But is there another way I could write the equation of the line for theta equals 4 pi over 3? Pi over 3. So just know when you're checking your answers, if you don't see theta equals 4 pi over 3, your answer's not wrong, excuse me, but they may write theta equals pi over 3. It's still an equivalent. It's an equivalent line in polar. Yes, Lisa. Yeah. Mm-hmm. because the equations of lines in polar in the form of theta equals. Okay. Now you have to check to see where your dx d theta is not equal to 0 to confirm. We don't know if these are our final answers or not, because remember this is where we also need to verify that your dx d theta is not equal to 0 here. So when I go to find my vertical tangent lines, I'll know exactly where dx d theta is equal to 0. So now remember, in polar, x is equal to r cosine theta. So I can plug in my 1 minus cosine theta for r. So x is equal to cosine theta minus cosine squared theta. So I can find my dx d theta. So what's the derivative of cosine? The derivative of cosine is what? Negative sine. Minus what rule am I going to have to use here? Chain rule. So this is going to become minus 2 cosine theta, and then the derivative of cosine theta is going to be negative sine theta. So I clean this up and set it equal to 0. 0 is equal to negative sine theta plus 2 cosine theta sine theta. Now how do I solve this particular trig equation? What can I do? Factor out a what? Sine theta. So I factor out a sine theta, that's going to give me a negative 1 plus 2 cosine theta. Now I'll set each factor equal to 0, so sine theta is equal to 0, 0 is equal to negative 1 plus 2 cosine theta. So now where is sine equal to 0? Sine is equal to 0 where? When theta is equal to what? 0 and pi. Do I have to write the pi? No, because would you agree with me if you look at your unit circle, when I look at the equation of my line theta equals 0, it's right here. But isn't that also the same equation for theta equals pi? So when you write 0 and pi as equations of lines in polar, it's actually writing the same equation twice. So this is, remember, the same equation as 0. So all you really need to write is theta is equal to 0 there. So I need to find out where is cosine of theta equal to a half. So where is cosine positive? Cosine's positive in quadrants what? 1 and 4. So then it's going to be theta is equal to what? Pi over 3 and 5 pi over 3. So again, are any of those answers where my dy d theta is equal to 0? Only 0. So which one do I have to reject? 0. So guess what you just found here? You found your what? Singular point. So my singular point, remember, is where my dx d theta and dy d theta is equal to 0. And that's occurring at theta is equal to 0. So in your answers for your vertical tangent lines are occurring when theta is equal to pi over 3, and then theta is equal to 4 pi over 3 and 2 pi over 3. So any questions on how you can find vertical or horizontal tangent lines in polar? Yes, Scott. Because if you look at the equation of a line in polar, because that's what we're finding, theta equals 0 is the equation of your polar axis. So is theta is equal to pi. It's not that I'm rejecting it. It's certainly a solution. However, it's the equation of the same line. It's the same line, exactly. So that's why. It's not that I rejected it, it's just as repetitive. Yes, Rashawn? Yep, so I'm not done yet. So okay? So again, singular point. So a point has an r comma theta value, correct? So an r comma theta. So when theta is equal to 0, what's the r value going to be when I plug it in? Well, cosine of 0 is what? 1, and 1 minus 1 is 0. So if you look at the graph of this cardioid, this is going to give you a visualization as to what that singular point is. That origin is typically where a singular point may occur. It's where that indentation of that cardioid is happening. It's kind of got that little divot right there at that point. That's what they're calling the singular point. It's where your dx d theta and your dy d theta are both equal to 0. All right, kind of got that little divot in there. Yes,
What I meant is on the point on the graduation,
no, a line is not a point. So the directions are asking for horizontal tangent lines and vertical tangent lines. And then it's asking for a point. In polar, the way you write equations of lines is in the form of theta equals. If theta equals the angle, that's the way you write the equation in polar, of a line in polar. Remember that from last year? All right. Okay, so let's take a look at tangent lines to the polar curves at the origin. So again, when you talk about the tangent lines to the polar curves at the origin, again, we did our dy d theta over dx d theta. So again, remember, when you've got a tangent line to the pole, that's going to be occurring when your r values are equal to 0. So when you have a tangent line to the pole, it's when r is equal to 0. So once you find your dy d theta and you get your dx d theta, you plug in 0 for r, and you simplify, you're left with sine over cosine, which again turns out to be the tangent of theta. All right? So when you're trying to find tangent lines to the pole, again, you want to make sure that it passes through the pole, so that means that the passes through the origin, or the pole. And if your dr d theta is not equal to 0, and theta equals theta sub 0, then the tangent is tangent to the curve of the origin. So basically what it's saying is that when you want to find your solving tangent lines at the origin, r is equal to f of theta. You want to make sure that your r is equal to f of theta, or that your f of theta is equal to 0. Because r has to be equal to 0 in order for this line to pass to the pole. This may happen for more than one value of theta. So you may have more than one tangent line to the origin. So let's take a look at this one. Sketch the polar curve at r is equal to sine of 3 theta, and then find your polar equations. First of all, graphically, what is this going to be? A rose with how many petals? Are you going to have a petal on your polar axis? No. Again, this is a sketch. So with 3 petals, here's 1, here's 2, here's 3. And I know the length of each petal is what? 1. So what I'm trying to find is I'm trying to find the equation of my tangent lines at the pole. So like right here and right here, for example. That's what I'm trying to find. So when you're trying to find the equation of your tangent lines to the pole, you want to make sure that r is equal to 0 and your dr d theta does not equal 0. That's how you find your tangent lines at the pole. So I need to set my equation equal to 0. So sine of 3 theta is equal to 0. Now you got to remember how to solve equations like this back in script. Substitute x in for 3 theta, yeah, so we can let x be equal to 3 theta. So sine of x is equal to 0. So where is sine equal to 0? Sine is equal to 0 where? At 0 and pi. So this is where you have to do your general solution. Remember, you bring it back in. Your 3 theta is equal to 0. Is it plus 2 pi k or plus pi k? 2 pi k. When is it just plus pi k when you're solving your trig equations? Tangent or cotangent, exactly. So I divide by 3, so theta is going to be equal to 0 plus 2 pi over 3 times k. I call this the good news, bad news scenario. When you have these general solutions, remember we ended up with 2 places where sine was equal to 0, at 0 and pi. If I just use this one general formula, will it pick up all of the solutions? No. Remember, you have to consider the second angle as well. When is it the good news scenario? You don't have to consider that second solution when it's an equation in the form of what? Well, which trig functions have which trig functions have a period of pi? Tangent and cotangent. So if you were solving a trig equation with a general solution to just pi, you'd only have to consider one. One of your solutions would pick up all the angles. So this one, you also have to consider where your sine of, you have to take your pi and set it equal, no, 3 theta is equal to pi plus 2 pi k. And then I solve for theta, so theta is going to be equal to pi over 3 plus 2 pi over 3 times k. Remember what you do at this point? You start plugging in values for what? K. So starting with 0. So theta is going to be, so I plug in 0 for k, one angle is going to be what? 0. If I plug in 1 for k, that'll give me a 2 pi over 3. If I plug in a 3, that'll give me an angle larger than 2 pi. We're just looking at angles between 0 and 2 pi. So we good so far? So now let me use my other solution. So if I plug in 0 for k, one answer would be what? Pi over 3. If I plug in 1 for k, that's going to give me a what? Pi. If I plug in 2, that's going to give me what? 5 pi over 3. And then I know I'll be larger than 2 pi. Are any of these repetitive? Right, so I don't have to state, remember, I don't have to worry about stating the 5 pi over 3 because it's the same as 2 pi over 3. Are any others repetitive? 0 and pi. Again, the line theta equals pi and a equals 0, they're the same one. So again, you don't have to write it twice. Yes, Rashawn?
There was a 4
You mean when I plug in a value for k here? If I plug in this one, so there should go. Well, you're right, I did skip one, but is 4 pi over 3 going to be equivalent to pi over 3? Yeah. So those are my 3 places. Alright? So any questions on where I got those angles from? And again, now you have to assure that, remember, your dr d theta is not equal 0. So now what you have to confirm is that your dr d theta is not equal 0 at any of those particular angles. So what is your dr d theta going to be? Well, if r is equal to sine of 3 theta, what is your dr d theta going to be? 3 cosine of 3 theta. So now we have to find where 3 cosine of 3 theta is equal to 0. So cosine of 3 theta is equal to 0. So where is cosine equal to 0? Cosine is equal to 0 where at pi over 2 and 3 pi over 2. Again, I have to do my general solution. So 3 theta is equal to pi over 2 plus 2 pi k. Divide by 3, and over theta is being equal to pi over 6 plus 2 pi over 3 times k. How this one? So now if I plug in 0 for k, one of my angles is going to be at pi over 6. If I plug in 1 for k, remember I'm just going to go ahead and write this as my common denominator now, 4 pi over 6. So plugging in 1 for k, 4 pi over 6 plus pi over 6 is going to give me a 5 pi over 6. If I plug in 2 for k, that's going to give me 8 pi over 6 plus pi over 6, which is going to give me 9 pi over 6, which is a 3 pi over 2. And then finally, 3 for k would get me larger than 2 pi. Would you like to consider the other place? Yes. So then I have to take my 3 theta, set it equal to 3 pi over 2 plus 2 pi k. Multiply by a third, so theta is going to be equal to pi over 2 plus 2 pi over 3 times k. So if I get my common denominator, it's going to be 6. I'll be 3 pi over 6 plus 4 pi over 6 times k. So let's see. When k is 0, I've got pi over 2. When k is 1, I have 7 pi over 6. When k is 2, I have 8 pi over 6 plus 3 pi over 6, which is 11 pi over 6. And then I know I do larger than 2 pi. So at any of these angles, are there any places that overlap where your r value was equal to 0? No. So then I know that my solutions are going to be 0, pi over 3, and 2 pi over 3. What a great trick to do. Who thought you ever need to do that? Yes, Kevin. So what we found, if you graph this line, theta equals 0, theta equals 0 is the equation of polar axis. So that's your tangent line to the pole. Theta equals pi over 3, that's the equation, another line of your tangent line to the pole. Theta equals 2 pi over 3 is another equation of tangent line to the pole. When I say tangent to the pole, you're talking about to the curve. It's only going to touch the pole. Yeah. But the tangent line point is at 1. Not for this particular curve. Because it's got the condition where it's passing through the pole as well as its tangent to the curve. It's only going to intersect at 1 point. There may be others that are passing through the pole, but it's not tangent to the road. That means that. That makes sense? Arc length. You have 3 arc length formulas you have to remember. Again, we've done the one in function mode, we've done the one in parametric. You also have to remember your arc length formula for a polar. So now your bounds are going to be angles from alpha to beta. So you're dealing with the distance around the polar curve. It's going to be the square root of your f of theta squared plus your f prime of theta squared d theta. Just to review, your 3 arc length formulas. There's 3 of them you have to remember. The first one is in rectangular, when you're dealing with x's and y's. Again, your bounds are going from a to b. Square root of 1 plus your dy dx squared dx. So if you're dealing with a curve in rectangular, there's the arc length formula, distance around a curve. Parametrics. That's when you're dealing with x of t's and y of t's. Again, you're going from a to b. Square root of your dx dt squared plus your dy dt squared dt. And then finally the last one, polar. You're dealing with r and theta. The arc length would be from alpha to beta, square root of f of theta squared plus f prime of theta squared, d theta. So you're still doing the same thing. You're finding the distance around. It depends upon which set of equations are given to you, whether they're polar equations, parametric equations, or rectangular equations, which one do you use? Beta. Beta, uppercase B, just represents an angle. Beta, alpha to beta. How did you do it? Okay, so let's take a look at this formula right here. So let's find the distance around the entire cardioid. So again, what we're trying to do is calculate again. Here's my cardioid. So again, remember the cardioid has symmetry with respect to the polar axis, so I know it's going to be reflection over your polar axis. So, first of all, let's talk about your bounds. To create the entire cardioid, you're going to start at 0. What do you think that upper bound would be? 2 pi. So f of theta is just my original equation, r is equal to 1 plus cosine theta. So r squared would be 1 plus cosine theta to the second power. So then your dr d theta would simply be what? What's the derivative of 1 plus cosine theta? Negative sine theta. So it's going to be the square root of 1 plus cosine theta squared plus negative sine theta squared d theta. And again, if these are calculator questions, typically a lot of polar will be calculator questions unless they are not too bad to integrate. All right, now when you take a look at in your calculator, for these problems you can remain in function mode. All right, so again, I'm under my y equals. I'm going to type in 1 plus cosine. Make sure you're in radian mode. Though. You've got to make sure you're in radian mode. I'm going to type in my r. I'll type in my dr d theta, which is my negative sine of x. Go back to my home screen. So again, I'll go to my alpha window, integrate, 0 to 2 pi. Square root of what I have under y1 squared plus alpha trace y2 squared. So the distance around this curve will be 8. All right, so any questions on, again, using that arc length formula? All right. Okay. We're going to go ahead and skip over B, so we can have time to talk about area. You found back in chapter 6, we spent lots of time calculating area between curves, area within curves, back in for rectangular. Now we're going to talk about the area in polar. Now, if you remember, we talked about area under curves back in chapter 6. We were dealing with area of rectangles. We were doing Riemann sums, and we started calculating the area of all the smaller rectangles. So if you're dealing with polar curves, when we start breaking up these regions into smaller and smaller parts, instead of dealing with area of rectangles, you're dealing with pieces of a circle. So if you remember back from geometry, we talk about sectors. So what's happening is instead of adding up all the areas of different rectangles like we do in rectangular form, we're adding up all these little smaller and smaller area sectors. Sectors are like a piece of a pie. They're a piece of a circle. So the smaller and smaller I can break up this region, the more accurate I can get to the area within the polar curve. So if you remember, the area of a circle is pi r squared. So the area of a sector is, again, depending upon what this interior angle measurement is, it's theta divided by 2 pi times the area of your circle, pi r squared. So what's happening is you're only finding the area of a portion of the circle. So then the area of your sector, I can cancel out the pi's, is equal to theta over 2 times r squared. So then the way we're going to find the area of polar curves, because again, I'm adding up all these different areas of sectors, is I'm going to find the antiderivative from alpha to beta of 1/2 r squared d theta. So that's the area formula we're going to use when it comes to calculating area of the polar curves. I'm sorry, what? Where's the left? Where's the left one? Well, your theta values are going to be when you integrate your alpha to beta. Because remember, you're taking the derivative with respect to beta. This is your formula right here. This is basically just proving what a formula comes from. This is your formula you have to remember. Alright, that's the formula you have to remember. The 1/2 r squared. Alright? Okay, let's move on here. We gotta move on. We got a lot to do in 2 minutes. Yes, a lot to do.
Are we never going to take notes again?
Nope.
This is the last time ever going to take notes. That seems more effort.
So, this may answer your question a little bit. Remember, when you're dealing with, this may answer your question a little bit about where the theta went. Remember, you're dealing with these equations in polar in terms of r and theta. So remember, your equations are r is equal to, let's say, 1 plus cosine theta, Kevin. Another way you could write this would be f of theta is equal to 1 plus cosine theta. So maybe that kind of affects what happens to theta in that particular formula, instead of writing terms of theta equals r. Okay. So when you're dealing with your area formula, remember it's going to be from alpha to beta of 1/2 f of theta squared d theta, or from alpha to beta of 1/2 r squared d theta. The tricky part about doing these problems in polar is determining the bounds. Just like when you're doing area problems in rectangular, you've got to get a picture. If the picture's not given to you, you've got to sketch the region. You're going to draw an arbitrary radial line, and I'll describe that more in a minute, from the pole to the boundary curve r is equal to f of theta. Some of the bounds are going to be more obvious than others. And the question you want to kind of ask yourself, over what interval of values must theta vary in order for the radial line to sweep out the region R? And like I said, we'll do some diagrams to kind of illustrate that in a minute. Your answer in step 3 will determine the upper and lower limits of integration. Like I said, sometimes the bounds are very obvious. You don't have to worry about drawing the radial line and asking yourself, but what area will you have to sweep it out? Find the area of the region. Again, here it's just in the first quadrant that is within the cardioid of 1 minus cosine theta. So it's a cardioid. I know cardioids will have the indentation at the pole, and the majority of the cardioid is going to be where? I know the symmetry is where? The symmetry with respect to what? Polar axis. So which direction is the cardioid going to be facing? Is it going to have majority of the side on the positive or negative side of the axis? Negative. So just a sketch. So again, I want to find the area of the region just in the first quadrant within the cardioid. So this is the region I want to calculate the area for. So now when we talk about this radial line, starting at the pole, here's one radial line. Imagine taking this line, and again, because these graphs are rotations, so I'm taking this line and I'm going to rotate it up here to help me find my bound. So since I'm just in the first quadrant, what do you think my lower bound is going to be? My lower bound will be a what? 0. My upper bound will be a what? Pi over 2. So to find the area,
So that's 0 to the left.
yes, for pole axis. Yes. So the area is going to be from 0 to pi over 2, 1/2. What is r equal to? R is equal to what? 1 minus cosine of theta to the second power d theta. So what constant can I make out? 1/2. I am going to have to multiply out this 1 minus cosine theta. So it'll be 1 minus 2 cosine theta plus cosine squared theta d theta. Integrating the 1 is not too difficult. Integrating the 2 cosine theta is not too difficult. But it's been a while since we've integrated these cosine squares. To kind of get you back to your other favorite chapter, chapter 7. This is where, remember, to integrate cosine squared of theta, you had to remember the double angle formula for cosine of 2 theta. Oh no. Remember, cosine of 2 theta, remember, was equal to what? 2 cosine squared theta minus 1. So remember, if I solve for cosine squared, it's going to be cosine of 2 theta plus 1 all over 2. Remember that back? So remember the double angle? Remember that if you know the double angle for the cosine squared, sine squared is very similar, except it has a what? The minus. It's a subtraction. So remember, when you're dealing with, because the u sub's not going to work on this cosine squared. So this is where you're going to have to do a substitution, replacing that cosine squared with a cosine of 2 theta plus 1 all over 2. So my area is going to be 1/2, 0 to pi over 2, of 1 minus 2 cosine theta plus cosine of 2 theta plus 1 all over 2 d theta. So now let's integrate. Integral of 1 is going to be a what? Theta. Integral of a minus 2 cosine theta. So it'll be minus sine theta, minus become a plus. So plus 2 sine theta. I gotta do my little chart. Remember your little chart? So your integral of cosine is going to be sine. You're right, so it should be minus. I gotta do my little SCFC thing. Alright, so now let's take a look at so first of all, let me take care of the obvious one. Let me take care of this 1/2. That's going to be a plus what? 1/2 theta. So now let me talk about how I'm going to integrate cosine of 2 theta all over 2. So I know I can yank out that 1/2, which is going to give me cosine of 2 theta. So I'm going to have to do a u sub. So u is equal to 2 theta. du will be a 2 d theta. So what constant am I going to yank out? I'm going to yank out a what? 1/2. So this is going to turn this into a 1/4 times cosine of u du. And then your integral of cosine is going to be a what? Sine. This is going to be plus 1/4 sine of 2 theta. It's been a while. So now I have to evaluate my bounds. Where my bounds are going from pi over 2 to 0. So 1/2 times, plug in my upper bound, that's going to be pi over 2. Sine of pi over 2 is what? 1, so that's going to be a minus 2. 1/2 times pi over 2 will give me a pi over 4. Pi over 2 is 1. And then pi over 2 times 2 is a 1. And I know sine of pi is 0. And do I have to consider the 0? That goes to 0. That goes to 0. That goes to 0. That goes to 0. Can I leave this alone at this point? Yes, you can. Yes, you can. If you were to actually simplify it, you would end up with 3 pi over 8 times 1. But like I said, you can leave that alone. Most of these, unless the integration is straightforward, a lot of these are going to be calculator problems. All right? But I wanted to make sure I did this one with by hand because it's been a while since you've had to do that cosine squared integration with that double angle substitution. Good solution from last year?
Yeah.
So any questions on example 5? All right, let's take a look at, now this one's asking you for the entire area with the cardioid 1 minus cosine theta. We've already sketched the cardioid. So again, I know my area formula is going to be the integral from alpha to beta of 1/2 r squared d theta. So again, here's that radial line at the pole. To rotate around to find the area within the entire cardioid, what do you think my bounds are going to be? It's going to have to go from what? 0 to pi. In terms of your calculator, these are polar curves. Change your mode into polar mode. Polar. Now I'm doing all this in pre-calc. Now it should be all hitting the thing. This is why you think it's all in pre-calc. Mode. Remember, guys, how you change your mode on the calculator. You go down to your mode, change it to polar. That's the third option over. When you hit your y equals screen, it now looks a lot different. It's on the form of r. So r is equal to 1 minus cosine theta. When you hit x now, it's a theta button. And if you change it to parametric mode, you'll get your t. So, again, now I can integrate. So alpha window, integrate. I can go from 0 to 2 pi. I can do 0.5, or I could have put the 1/2 on the outside of your interval. And again, now I can go to my alpha trace, and now instead of my y sub 1, it's in terms of r. So I end up with 4.712. If you're dealing with, guys, these problems in polar, you will leave your calculus in polar mode. The only time, if you're dealing with any kind of polar area question, you may have to change it back in the function, is to find your bounds. Remember back when you were doing the area within the function curves? You were using your calculators to help you figure out the intersection points. In polar mode, if you go under second trace, you do not have as many options in polar mode on your calculators as you do in function mode. All right, but otherwise, if you're dealing with area in the polar, you just leave it in polar mode. So now find the area within the shaded region. So here, they've already given you the graph, and some of these they'll just give you the graph. The trick is getting your bounds. So again, I know my formula is A is going to be equal to my lower and upper bound of 1/2 r squared d theta. So now again, you've got your radial line here to here. So we're trying to calculate the area of just the right side of this cardioid. So what do you think the lower bound is going to be? Would I say 3 pi over 2 though to pi over 2? What's another way to state 3 pi over 2? Negative pi over 2 to pi over 2. So my area is going to go from negative pi over 2 to positive pi over 2 of 1/2 times the 1 minus sine theta squared d theta. And for essence of time, again, you can type this in the calculator here. There's your interval setup. Now, when you're dealing with roses, I'm going to shade it right there. It's just the one petal here. When you're sketching roses, the direction that the graph is going, it's going in rotation like this. It starts at the pole. It travels below the polar axis around. Then it goes up to create the second petal, hits the pole again, comes back around, goes down. So when you're dealing with the roses, here's the rose cosine of 2 theta. Again, what I'm trying to do is I'm trying to calculate the area of just one petal. And with roses, you're going to use symmetry to help you come up with the area within the petals. Because if you know the area of one petal, you can find the area of the entire rose. Because remember, these petals are all symmetrical. So as long as you can find the petal of one rose, and we'll do one in a minute, then you can just multiply by the number of petals and it's asking you the area of the entire rose. Yes, Grace?
Could you just do it from 0 to pi over 2?
No, because of the operation happening on theta. Because remember, you're going to, when you plug in pi over 2 in here, it changes the angle measurement. So the trick to find your bounds, this petal is created when r is equal to 0, travels around, and gets back to r is equal to 0 again. So that creates one petal. So what you're going to have to do to find your bounds is you have to take your cosine of 2 theta and set it equal to 0. Because we want to know when is your r equal to 0. Yep. No. Because what happens if you plug in 2 pi for theta? That's the trick, because you have the operation happening on theta. So it's not like the cardioid, it's not like the limazon, because you have the operation happening on theta. So now, where is cosine equal to 0? Cosine is equal to 0 where? Pi over 2 and 3 pi over 2. So then I have to do 2 theta is equal to pi over 2 plus 2 pi k. Here it is all over again. You have to know, remember, to create one petal, it starts when r is equal to 0, and it travels around back to 0. So we need to know the theta values that are going to give us the r values equal to 0. So you have to take your original equation and set it equal to 0. So where is cosine equal to 0? Cosine is equal to 0 at pi over 2 and 3 pi over 2. So this is where you have to do your general solution again. You have to bring your 2 theta set equal to pi over 2 plus 3 pi k. So then what's theta going to be equal to? Theta will be equal to what? Pi over what? Pi over 4 plus divided by 2, that's going to be pi k. So then what in your case, theta will be equal to pi over 4. So if I consider this one, the 2 theta is equal to 3 pi over 2 plus 2 pi k. Divide by 2, I end up with theta is equal to 3 pi over 4 plus pi k. So I end up with theta is equal to 3 pi over 4, and then I end up with, so these are my theta values, pi over 4 and 3 pi over 4. Now I'm not going to go through and find my entire list. So now look at your graph. Yes, Scott? Yeah, you can. writing it down so you didn't see it. Yeah. Right. I mean, you have to know that this is pi over 4. Whether you can instinctively do it in your head or you have to write it down. You have to know that this is pi over 4.
Right. Cosine. We know what cosine theta and cosine theta.
Again, as long as you know that this is pi over 4. Whether it's in your head or you've got to write it down. I don't care. But you've got to know that this is pi over 4. So now this is pi over 4. Using your idea of symmetry, what is this down here going to have to be? Negative pi over 4. So guess what your bounds are going to be? Great. So from negative pi over 4, your area is going to be equal to your lower bound of negative pi over 4 to pi over 4 of 1/2 times the cosine of 2 theta to the second power of 2 theta. Right. Like I mentioned, if you can find the area of one petal, you can find the area of the entire rose. So this is where it's convenient to use the idea of symmetry and take multiples of the region that is repeated. So what graph do we have with r is equal to 2 sine 3 theta? This is a what? A rose with how many petals? 3. So 3 petals. Again, I'm going to find the area of one petal and multiply by 3. Again, like I mentioned, you start at 0, and that's how the petal is formed. So again, you have 2 sine theta, 3 theta is equal to 0, because you have to find your bounds. So you have sine of 3 theta is equal to 0. Well, sine is equal to 0 where? Sine is equal to 0 at 0 and pi. So then 3 theta is equal to 0 plus 2 pi k. 3 theta is equal to pi plus 2 pi k. So when I divide by 3, I know that theta is equal to 0, theta is equal to pi over 3. So what do you think your bounds are going to be? Your bounds are going to go from where? Look at your theta values you got. Theta is going to be what? Again, I'm only looking at the angles in quadrant 1. 0 to pi over 3. So your area is going to go from 0 to pi over 3. 1/2 times your 2 sine of 3 theta squared d theta. And again, what would you have to do with this area? You have to then take this area and multiply it by 3. Because remember, this is just the area of one petal. Yes, yeah. I mean, for these you don't, because you're just dealing with the area of just the one petal, so I don't need to generate my whole entire list. But again, because you have an operation on theta, anytime you have an operation happening on theta, when you're solving your trig equation, you have to do your second solution. Because basically what happens, yes, it does. But basically, again, what happens is if I plug pi over 3 in for theta into my original equation, that gives me the sine of pi, which is 0, which is what the equation I said is equal to. So you're looking at places where your r value is equal to 0. And there's more than one. Again, I don't need to solve them for these because, again, I can plug in 1, 2, 3, and so on. Because if this coefficient is 3, instead of having just 2 solutions, you'd end up with triple as many 6 in that region from 0 to 2 pi. The coefficient was 2 theta, you'd end up with 4 solutions from 0, whereas typically you only have 2. Well, it's just theta. Yes, Brian?
So, if you wanted to find the survey of one petal, you couldn't just, is it not possible to do the integration of 0 to 2 pi divided by 3?
No, because it doesn't go as long. It's to do a full rotation. Again, to get a full pedal, notice you're only going from 0 to pi over 3. So you're not having, because again, it's 3 times theta, not just theta. So if you were to plug in 2 pi, what would happen, it would be 3 times 2 pi, which is 6 pi. So that's the issue.
But you didn't do like 2 pi over 0 and 2 pi over 3, or that's not.
But you what?
Do 0 and 2 pi over 3. Because then it'd be like,
Well, what you could do, you can use your calculator to help you see. So for example, if I type in 2 sine of 3 theta, and I change my window, going from 0 to pi over 3, you'll see where you get just one pedal. So if you have your calculator, you can always, which we'll talk more about on Monday, you can double check that you have your bounds correctly. Obviously, we change my window so you can see it better. So my R value is 2. So there you can see the one pedal. But if you go from, I didn't change my bounds here. If I change this from 0 to 2 pi over 3. What?
We're still recording, by the way.
I know. Stop it, yeah. I know. They'll put up anymore. You know, let's